This section explains what the prelude sets up and what debt it names. Higher category theory earns its complexity by refusing to identify what is merely equivalent. The prelude states the debt. Ordinary categories treat isomorphic objects as interchangeable up to something, and that up to something is exactly the structure classical language discards. Szysinski's move is to make the discarded structure primary, spaces of maps rather than sets of maps, coherence rather than equality. He then shows that the resulting theory is not harder, but more honest, its constructions falling out of homotopical algebra already in hand. What the chapter is for, in the book's arc, it announces that infinity categories will be built, not postulated, from model categorical material, so every later abstraction carries a computational shadow. This section explains how homotopy theory is set up here as a calculus of lifting. You fix which maps you want inverted, and orthogonality, meaning the left and right lifting properties, together with functorial factorization, generates cofibrations and fibrations as consequences. A model structure is scaffolding, machinery that makes the localization computable, and derived functors, well behaved. The ex nihilo construction then reverses direction. On presheaves, you declare the cofibrations to be the monomorphisms, and a model structure falls out of the chosen data. So the homotopy theory of infinity categories arrives in Chapter 3 as one instance of that construction, already covered by it rather than built to order. Absolute weak equivalences close the chapter as its seed for Chapter 4. Nothing here is original, and the arc ends by swallowing it. Chapter 7 will include homotopical algebra within the theory of infinity category theories. This section follows a single dial through the whole chapter, which horns a simplicial set is required to fill. Demand every horn, capital lambda sub kn, and you get can complexes, the infinity groupoids, where every arrow inverts. Demand only the inner ones, and you get infinity categories, where composition still exists, but stops being canonical. Szysinski runs. Chapter 2's abstract machine on simplicial sets at both settings, producing the Conquilin structure and then the Joyal structure. The labor is proving that each structure's fibrant objects coincide with the handmade definition, a definition meeting its homotopical characterization. The reward is a translation table. Whitehead's theorem for complexes reappears for infinity categories as fully faithful plus essentially surjective. Infinity groupoids sit inside infinity categories exactly as sets sit inside categories, and Kahn's X-infinity construction is where coherent inversion becomes visible. This section explains what a presheaf on an infinity category is, and why the definition is given externally. A presheaf on an infinity category cannot be a functor from C, opposite into infinity groupoids, without an infinite tower of coherence data. Szysinski's move promotes the category of elements from construction to definition. The fibration from C over F down to C over F down to C already knows F. The assignment sending F to C over F down to C over F is fully faithful into cat over C, and its abstract characterization is a right fibration. So P of C, the right fibrations over C, is the presheaf infinity category, carrying no coherence bookkeeping whatsoever. That is what externally means the structure lives in the map down to C, never inside a functor. Everything the chapter then reaches is reachable, because the definition stayed strictly, 1, categorical. The contravariant model structure, final maps, mapping spaces as homotopy fibers of slice fibrations, and Quillen's theorems. This part explains how an externally indexed family of infinity groupoids becomes a single internal morphism. External indexing becomes an internal morphism once the family has a classifying object. Chapter 4 presented an A-shaped diagram of infinity groupoids as a left vibration over A. Here, Szysinski constructs S, the infinity category of small infinity groupoids, carrying a universal left vibration, written P univ from S pointed to S. Every left vibration is a pullback of that single one, so the phrase functor from A to S and the phrase left vibration over A coincide by definition. The chapter's labor is to upgrade that syntactic coincide by definition. The chapter's labor is to upgrade that syntactic coincidence of mapping spaces. This is the same move as omega classifying subobjects. What it buys is the Yoneda embedding and a Yoneda lemma, which Szysinski insists is at bottom a cofinality statement, lemma 5.8.11. This section explains how one representability condition generates adjoints, limits, colimits, and con extensions all at once. A presheaf is representable exactly when its infinity category of elements has a final object. An adjoint is that same condition stated in families. Szysinski says this outright, and the rest of the chapter is that single sentence unfolded. Because the Yoneda lemma from chapter 5 is already in hand, adjunction can be defined the classical way, by a functorial equivalence between the mapping space from x to v of y and the mapping space from u of x to y. Limits, colimits, and con extensions then arrive as the fiberwise and relative cases of that same representability test. The chapter's office in the arc of the book is to show that infinity categories demand no new category theory, only the old definitions read internally. A footnote quietly settles that this naive-looking definition agrees with Lurie's heavier one. This section explains how homotopical algebra is organized around one operation, inverting maps. Inverting maps is the whole subject. The chapter reverses the usual dependency. Model structures, fibrant objects, and derived functors stop being foundations for homotopy theory and become calculational devices for a localization whose meaning is already fixed by a universal property. The pivot is Proposition 7.3.15. Every infinity category is the localization of an ordinary category. Localization therefore generates the objects rather than acting on them. Vibrations then earn their place only by making that universal property computable. Reedy fibrant approximation lets limits commute with weak equivalences, and right-derived functors fall out as the formula. Quillen's theorem, B, Waldhausen approximation, and derived adjunction all return as corollaries, the test that the reversal was the right one.